irrational numbers, and I want us to see how an irrational number is something you can't make a fraction out of and express. Like square root of 2 is 1.414 and it's a decimal that keeps going forever, or the number pi is 3.14 and it keeps going on forever. Even though these numbers are things that go on forever and you could never actually write them down, I want us to see visually what an irrational number is and sort of begin to understand how even though you can't write the number down because it's an infinite decimal, it actually has a shape and a proportion geometrically. So, the first shape we could take a quick look at is a circle. Understanding where the number pi came from, the number pi is an irrational number, and trying to understand where the number comes from. So if you take a circle and compare it to the diameter, that's really where the number pi comes from. So let me make the diameter green and I'll make the circle red. So when I look at the number pi, or when I calculate it, it's really the circle and seeing how many times it would divide into the diameter, into the line. And it's always going to be 3.14. So in essence, it's saying I could put that green line 1, 2, 3, and then a little bit extra. 3.14, and it's continuing infinitely. So you could never really truly get it. Infinity, or even the circle, is a wonderful metaphor of something that you can kind of grasp and begin to understand, but you could never truly know. You could never truly get there. It's like an ideal. So really we get the number pi by dividing dividing the circle by how many times the diameter will fit around it. And it seems so much more magical than that, but that's really where the number comes from. So we can see it visually, the number pi, because it's related to this circular shape. And the definition of a circle is the center point and the number of infinite points around it that are from the same distance, that are formed the same distance, which we would call the radius. And let's take a quick look at squares. We could look at cubed roots. That would be way more complicated in the 3D sense. But when we look at square roots and squares, we're actually talking about a square. So let's draw a square and take a look at how the diagonal is irrational. But we can draw it, we can construct it, we could build it. However, it's a number when you put it into a calculator is infinite, and it goes on forever and doesn't repeat. So if I take this square, it says regular, meaning all the sides will be the same, which will make this a square. What we learned about the Pythagorean theorem is if you take 1 squared plus 1 squared plus 1 squared, you get the hypotenuse squared. Our Pythagorean theorem says a squared plus b squared, the two sides squared, will always form a square in the diagonal. And it will be equal to that square, the sum of the two sides. So when I do that, I'll get 1 plus 1, which is the square root of 2, when I square root both sides. So we learn in mathematics that the diagonal of a square with sides that are the same, that are 1 and 1, will always be radical 2 times these sides. So if it were 10, it would be 10 radical 2. And what is that number, radical 2? So the number, when we put it into a calculator, we would see, I'll do that even though it's there, put 2, click the radical sign, and you get 1.41421, and it continues infinitely. So again, it's irrational. However, it's really just the comparison of across the diagonals of a square compared to the sides of a square. That diagonal will be 1.4 times, or 141%, if we're looking at it as percent. 141% compared to the side. So if the side's 10, it's going to be 14.14 for the diagonal. So it's an irrational number, but I always thought it was very interesting that we could use that diagonal, the square root of 2 diagonal, and we're going to make another square out of it. So now we have something that's flipped, because here we had 1 and 1 and radical 2, so now the new one has side of radical 2. The sides are the same. So when we connect the diagonal here, you can actually predict it visually, right? From here to here we said was 1. 1 plus 1 gives us 2. So now our diagonal of our bigger triangle the sides are irrational. So you can draw shapes with irrational numbers, 1.41 infinite number, and you can actually use that shape even though you can't write it down mathematically. Now when I compare the diagonal, this one will be 2. So it's saying this is 2 compared to the sides are 1.41, and it's an infinite decimal. So what we see is something's changing. One way we can actually prove this, I could see here this square is half the distance, so I've had 1 and 1. So really, let's use the Pythagorean theorem to prove it. The two sides are radical 2 squared plus radical 2 squared equals our hypotenuse squared. And square root of 2 times itself is 2, and we get 4. So the square root of 4 is 2 as we see it visually, but we can prove with the Pythagorean theorem that this diagonal is 2. So the first diagonal was an irrational number, but then we use that to create a square, and now the diagonal is a regular number, the number 2. What do you think is going to happen if I then use that number 2 and make a square? Well, we're going to have the same thing, right? It's just double the size of the starting one. So we're going to keep repeating back and forth with this pattern. Let me show you what I mean. So now I'm going to make a square that's the size of the new diagonal. And you're going to see that our sides and our diagonal will just repeat back and forth. So here was radical 2. Here the side was 1 and 1. And so then here the side was radical 2. And the diagonal was the number 2, 2 and 2. So what are we going to get here? Well, you can kind of see it, right? The green one is radical 2. There's going to be another one. There's 2 of them. So the new diagonal is going to be 2 radical 2. And we could do that with the Pythagorean theorem. 2 squared plus 2 squared equals c squared. 4 plus 4. So 8, so square root of 8 is 2 radical 2. So our new diagonal here is 2 radical 2. Our sides were 2 and 2. Our diagonal is 2 radical 2. So what we have is this repeating pattern where the sides started with 1. Now the new square sides was radical 2, then 2, then 2 radical 2. And we just keep multiplying by radical 2. So the next one's going to be 4, and then 4 radical 2, and then 4 radical 2 times radical 2 will be 8. So we're just going to keep alternating the sides, and the diagonals will go from rational to irrational, rational to irrational. And so even though it's an actual irrational number, we can draw the square or a diagonal out of that shape. So to me, it's kind of interesting that math works in such a way that sometimes you can't even imagine a number, but you could work with it, like x to the 4th power. We don't know how to visualize a 4th dimension. However, there are other times like this where even though you can't imagine the number, you could still draw like a circle related to the number pi, or a diagonal related to radical 2. So we can draw irrational numbers even though we can't write them down or get them in our calculator because they're infinite. Hopefully one day you could tell me what this all means and how we use it in more advanced math.